Hello, and welcome back to another video. In this video, we'll be building on what we've been working on in the previous videos of this series. If you remember, in this previous video, we ran into an issue with our time-step variant, delta t. When delta t reached over 0.5 seconds, our Python code and temperature profile ran into some issues when graphing. So today, we'll be using explicit differentiating, more specific, the Nicolson method, to illustrate a manner that we will not have a time-step variant issue. So as always, I've gone ahead and put our heat diffusion equation up here. You guys know this, we've been working on the past few videos. I've only flipped this around so that our, of course when we read it, we have our partial derivative of temperature with respect to time is equal to alpha multiplied by the second partial derivative of temperature divided by, with respect to delta x squared. So with that being said, let's go ahead and start this Nicolson method, right? So going based off of this heat diffusion equation, if you remember in our implicit differentiating videos, what we did for both of these iterations, we're going to do something similar. So for the left-hand side, we're going to keep it exactly the same to what we had, which is just simply comparing the two temperatures at the same position but at different time zones, or in different time increments. So we'd had t at j of n plus 1 minus t of j at n all over time-step variant delta t. Then, of course, again, we have alpha. And then this is where it gets a little tricky for what we're going to do for explicit. However, we're going to, very similar to what we did previously. If you remember what we ended up with t of j plus 1 time interval n minus 2 of t of j time interval n plus t of j minus 1 time interval n all over delta x squared. Alright, now what we're going to do differently in this explicit differentiating is that we're actually going to compare, so in order to get rid of the time-step variant issue, we're going to be comparing, for here we're going to be comparing these two positions at different time intervals. If we imply n plus 1, we're going to be able to get rid of that issue. So what I'm going to do is get the average of those two. So of course I'm going to add the second time interval and then divide it all by 2. So of course this is very similar. This is tj plus 1. You simply add 1 to the n, as well with t of j and t of j minus 1. Of course, this is also divided by delta x squared. Beautiful, there we have it. There is our starting equation. And then, like always, what we want to do is get our like terms on its correspondent side, get our n plus 1s and our n's on each side. And to do that, I'm just going to get rid of this delta t and delta x. So I'm going to multiply, oh, I almost forgot, we wanted 2 out here, right? Because we said we're going to get the average of these two, so divided by 2, we get the middle point. And what I'm going to do to get rid of, get them on their own terms is multiply out to this alpha. So on this left-hand side, we only get the numerator of tj n plus 1 minus tj of n. And of course, we're going to have alpha divided by 2, and then delta t, and then delta x squared as well. All right. That's a new term, and then we're also going to have this whole gibberish side of the equation without delta x squared. So t of j plus 1 time interval n minus 2 t of j time interval n plus t of j minus 1 time interval n plus t of j plus 1 n plus 1 minus 2 t of j n plus 1 and then finally plus 2j minus 1 n plus 1. That whole in brackets. That looks good, all right? And then, if you may recall, what we did in the second video previously, and what many books say to do, see, if you may recall, we have this term out here of all pretty much constants. Alpha, we're going to keep that as 1, again, delta x, 1 meter again, and then delta t is kind of what we're varying. So I'm going to go ahead and get rid of this and just give it a single term instead of calling it r, as we're going to go back into our previous collaboratory Python code that we used in previous videos. So I'm going to go ahead and call it a c, so as to not cause any confusion when we're later putting this into our code. So now what we can do is multiply this c out and get like terms on each side, right? So I'm going to start with n plus 1s on this left-hand side. So I'm going to multiply this c to these last 3 values and putting it over to this side. So z times t of j plus 1 at time interval n plus 1, of course. Then, actually, before I mess up already, so on the right-hand side, multiplied by z, we bring it to the left-hand side, becomes a negative z, right? So we have negative z of tj plus 1 and n plus 1. Then we have negative 2z, bring it over to this side, it becomes positive 2z. And if you call it's j at n plus 1, we also have j of n plus 1 here, so it's going to have 1 plus 2z. So plus 1 plus 2z of tj of n plus 1. And then finally, tj of minus 1. Multiplied by z, and again, bring it over to the left side so it gets negative. So we get minus z of tj minus 1 at n plus 1. Beautiful. So we have our left-hand side of the equation, and now we have to get it to the right-hand side. Again, all we do, multiply this out and add this to the right-hand side. So z, tj of n, j plus 1 of n. Then multiply by negative 2, bring out this positive 1 to this side, so we get 1 minus 2z of tj at interval n, right? Yep, and then finally, our tj minus 1 gets a positive, because it remains on the right-hand side, at time interval n. Beautiful, so there is kind of our final equation, right? So from here, what we want to do is work out a matrices, right? So if you may recall, we're still working with a bar, right? And we've given this bar many different increments, just so we don't know. And we know of 0, and it goes all the way to increment n. What we know is temperature at this first one and temperature at this last one, right? So we don't need to worry about these two. However, we're going to worry about all of these increments in here. It's n minus 1 amount of increments. If we're dealing with 20, there's going to be 19 different increments. Or 18, sorry. So we're going to have to write 18 different equations, one for each increment, or for each incrementation, right? So that we kind of get rid of this issue. And so what we're going to do is a matrix multiplication, right? What this looks like, we're going to have our list, our nouns right here, multiplied by this, and we get inside, right? Okay. So what goes where? Well, here, this is going to be our temperature, right? Our unknowns. So we're going to go from T1, because we know what T0 is. Again, we're starting at 28 degrees Celsius, so we know that, and we don't care about it, so we care about T1, T2, t3, t4, blah, 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 all the way to t of n minus 1, right? Because t of n, we also know what that is. We want to know temperature right before it. Sweet. Now, what we want to do is assign value to each of those columns and rows, right? So let's go ahead and start with T2. So if we were to multiply T2, what would happen? Well, we'd have 2. So we'd have minus z out, right? Then of T2 would have 1 plus 2z. Then finally for T1, we'd have minus z, right? Because 2 minus 1, z. Right? These are 3 columns, 1, 2, and 3. Then, let's go for T3, right? Plug in 3, negative z, and we'd have to switch over columns, right? As this is image multiplication, and it's multiplying throughout. So negative z for T4. Then for T3, we have 1 plus 2z. And then finally for T2, we'd have negative z. Okay. We can keep on doing this all the way to Tn of minus 1. I'm just going to do one more for T of 4. So if we'd have T of 4, let's be T of 5, we'd have negative z. And then we'd have 1 plus 2z for T4. And of course, minus 2z for T3. Then, of course, obviously, all these missing are all zeros, right? And also after here, there's nothing multiplied out, so that's all zeros in that row. And then for T1, what happens there? Well, if we multiply that out, we have T1, 1 minus 1 is negative 0, or T of 0, which we already know. And then plug that in here, we'd have 1 plus 2z and negative z. So we'd have 1 plus 2z of T2, and then negative z for T1, right? And if you may have noticed now, this is kind of a diagonal matrices, as it kind of multiplies out and it keeps going to the right. So with that being said, we've gotten this kind of figured out. What are our answers going to look like, right? What are we going to have? Well, again, let's start off with T2, and now we're looking to the right-hand side, right? So if we plug that in for T2, we'd have z, or let me put this down a little bit lower. We have z of T3 plus 1 minus 2z minus 2z of Tj of n, which is T2, plus we have z of T1, right? So we have for the second temperature, we can go ahead and do this for the third one. So we have z of T4 plus 1 minus 2z of T3 plus z of T2, right? Of course, we can go ahead and keep doing this. You may notice there is a pattern. So it becomes z of T5 plus 1 minus 2z of T4 plus z of T5. This goes all the way down to Tn minus 1. However, there are some issues with T1 and Tn minus 1. Why is that? Well, because we know what T of 0 and T of n are, right? So we can go ahead and kind of bring them over to the other side. So what T of 1 should look like, right? We should have z T of 2 plus 1 minus 2z of t1 plus z of t0, right? However, if you look over to this side, we should also have a minus z of t0 at the next time step. However, t0 at the next time step and the next time step after that and throughout any time is going to remain constant, right? So we can go ahead and bring this over to the other side and actually make that a 2zt0, right? So first hand remains the same. We have z of t2 plus 1 minus 2z of t1. And instead of adding plus z of t0, we're going to have 2z's, right? Because we're bringing this over to the right-hand side. 2z of t0, right? And then kind of the same idea here with tn n minus 1. What ends up happening is you see with this j plus 1, we know that at t of n, because n minus 1 plus 1 becomes simply n, t of n. We know what that is at the final, so we can go ahead and bring this over to the other side so that this becomes a 2z at the front. So that we have 2z of t, and then what is this going to be? We're going to have of t n, and then plus 1 minus 2z of tn minus 1 plus z of tn minus 2, right? This looks like 5, should be a 3. Alright. Looks pretty good. There is our matrix multiplication, kind of worked out, kind of simplifying what we're going to be doing. So with that being said and done, let's go ahead and plug this Crank-Nicolson method into Python code and see how the plot looks, right? How if delta t ends up being a limiting factor. So let's go ahead and do that. Hello, and welcome back to Collaboratory. Now that we've gone ahead and solved for the matrix multiplication on our whiteboard, we can go ahead now and plug that into our Python code so that we can go ahead and plot out the temperature profile for this bar over time. Before we go ahead and get started, I want to bring your guys' attention to the top. As I, from SciPy linear algebra, I went and imported this function solve_banded. We haven't used this before, so let me explain really quickly what it is. So it is a banded matrix, and it is helping us to work it out. As it explains, this is how this banded matrix is kind of seen, with the very first row not having the first value, and then the third not having the last one, right? So we're going to keep this in mind. And then, of course, you want to put some values in. You want a lower and upper limit, the values of A, B, and B, right? So with that being said, let's go ahead and get started. As always, we like to plug in our knowns at the beginning. So I'll just copy and paste that into here. The only differences are R, this is Z, I'm going to make this capital, and this is now divided by 2, right? A little different. You can go ahead and pull this up again. Also, we want the temperature, right? Make sure that's looking good. Run that through, make sure the temperature is good. All right, and we have our array. Cool. Get rid of this. All right. Now, what we can do is, of course, like we're explaining here, we want to have a list for our temperatures, and we're just going to start off with having them all as zeros, just to simplify it. So I'm going to call this a band, right? Or a band. We're saying numpy zeros, right? Zeros, and of course, how many columns we want. We want 3, and as for rows, we should want n. However, we know the left-hand side and the right-hand side of the starting temperature is 50 and 80 respectively. So it'd be n minus 2, as we know those two. So it should be 18. Then what we can do from here is go ahead and plug in our values for negative u, 1 plus 2u, and so on for them into the matrices accordingly. Right? So if we took a picture of what we worked on, go ahead and call a band. Start off with this negative z. If you look, it's going to be the first row or first column in the second row, right? So this looks like 0. And then we want this to fill this all the way up, right? So this is equal to negative z, right? And then for our second, we see for our 1 plus 2z, this is the one that goes all the way across. So this is on your first one. And we want it to go all the way across, right? So 0 all the way. This is 1 minus plus 2 times z, right? Then finally for this last negative z, we want it in this third column and everything except this last value, right? So what that's going to look like is so everything but the last value. So I'll go to negative 1, right? And what do we want? We want the third column all the way through to the last, right? That should be good. Oh, this clearly should be 2. Not even equal to anything. Negative z. Then this should be, get rid of the first one, right? Yeah, we don't want the first one. And then get rid of that. I think this should be good now. Alright, and then if we run a band, it should show us correctly. Let's see. Beautiful, there we go. So there we have it. For our first value, we have 0, like we said, because we don't want anything there. And then fold up with values of negative z. And then in the middle, we have 1 plus 2 times z for all of them. And then for the last one, we have negative z for all but the last one. Right? So this looks good. And make sure your z is right. We have alpha times dt. And if we change dt, let's go ahead. This is the reason why we did crank Nicolson, to make sure that dt does not change it. So if you run dt to be up to 1, let's see how this impacts our a band. Still looks good. Our z values are good, so we're good with the a band. Right? Now what we can go ahead and do and is plug in these equation, right? Plug in our knowns. We know have our a. Now what we have to do is plug in equation for b, right? So b, and then just gonna run through this. So z times temperature. We want this to be from 2. It should be 2 all the way through, right? We want 1 minus 2 times z, and then multiply that by temperature. We want this from the first and all the way through the last one, or second to last one, and then plus this last one. We have z times temperature. It should be all the way through to the last one. Right. Then, if you may recall, we had some issues with T1 and Tn-1 as an extra z t of 0 showed up and an extra one here showed up, so we have to go ahead and kind of encounter that into our code, right? So how that looks, b 0, and actually I think Yeah, this should be -2 as we're skipping over the last two, right? Not only the last one. This should be, we're going to simply multiply z times to and add it to it, right? So I'm going to say 0 plus z times, plug in temperature for that situation, or I can simply just put in T of 0, right? Or whatever, we'll figure that out later. Okay, well, this should be T of 0, so I'm just going to call it T of 0. Should work out. And then we should do the same with the very last one, so B of -1, right? Again, B of -1 plus Z. Now, however, we want to multiply it by n minus 2, so 1, -2. And that should be good for our B, right? Should just be -1, right? Pretty sure. Should be good. Well, what we can do to make sure this is right is plug in solve banded, right? So let's go plug that in. Solve banded. What do we need to plug in? Again, we need upper or lower and upper, right? That is, we have 3 to 1, right? Our AB is our A band, and our B is our B. Right? Should be good. Run that through. There is an issue. Okay, so sorry for the parameters. L and U, the upper and lower, are the number of lower and upper diagonals. So we don't have 3, we just have 1 and 1. Sorry about that. Those are just diagonals, so that should be good. Beautiful. And those are our values. Beautiful, amazing. This looks great. So now what we want to do here is the same concept we did previously, is simply run it through a for loop, right? So I'm actually gonna bring this back so that we can graph it out. Right? Alright, I'm gonna put it in here. Alright, that should be good. We can go ahead and I'm just going to grab this whole thing and then we can go from there. So for high and range, we want to keep it that way. The only thing we want to change is this B. Right? So we're going to put it. Our B values. Index all of these. Make sure. Right. We don't need this anymore. I don't think we need this anymore. So we have our I in range. We put in our B's. Our first and last, right? They need some difference. Oh, the actual value of temperature, right? we need the temperature. This is where the solve banded obviously comes in. Go ahead and delete this now. So this is going to be from first to second to last. We have solve banded. And we're going to have fig 1, add scatter. T is always your temperature. Alright, this should look good. If you come in, run this all over again. I'm going to actually change this dt back to 0.5 for now. Alright, 2, 3, 4, our A band. And here's our graph for temperature DT of 0.5. So that looks good, no issues. It just should look exactly like this should look, right? Maybe a little bit smoother, less curves. If we go ahead and way up, change this DT to whenever we went over 0.5, there's an issue, so just simply go to 0.6, see how it reacts with that. Beautiful, just as fine. Now let's just shoot it up for fun to 1. And we see it's not as beautiful, and then we don't have as many lines, but it's still what we need it to be, right? So it's looking good, and let's just do something obnoxious, 0.2, see how that looks. You can see we have reached a consensus that for any values of dt, even 1.5, it might look a little messy, but we are still able to get what we need. So there you have it, the Crank-Nicolson method, and the solve banded helps us achieve what we couldn't achieve previously. So thank you for watching, and I'll see you guys in another one.